Let's get to the meat of the matter. Let's try to solve the heat equation. So, general, we want to solve the heat equation. We're going to look for a temperature that goes from a domain and a time and gives us a real value. We have built up the equation. It takes the derivative with respect to time of Cv times the temperature minus alpha squared delta T equals to 0. And this has to be valid on all of omega, all the time. We also want to start with an initial condition, so we know that at time 0, the temperature has a specific value on every single element of omega. On top of this, we also want to impose some boundary conditions. So let's go into a specific heat equation. We take our domain, omega, to be the interval from 0 to L. So it's a subset of R. You can imagine this being a thin bar of something, and you want to measure the temperature every single point on that thin bar has over time. It's a one-dimensional problem because omega is 1D. Our boundary conditions will be at 0 and at L. Those are the boundary of our interval 0 to L. So we have to impose something. We're going to be imposing Dirichlet boundary conditions. So for every time, we'll impose a value of the temperature at 0 and the value of the temperature at L. We're going to call this U1T and U2T. So you can imagine that we want to solve for this thin bar from 0 to L, from time 0 to infinity. So we have this sort of infinitely long rectangle. We have imposed an initial condition at the beginning, and we keep track of the boundary condition all the time. From experience, we know that easiest boundary conditions are homogeneous boundary conditions. So there is where we're going to be starting at. We're going to impose homogeneous Dirichlet boundary conditions on the two sides of on all the boundary of our domain. That means at 0 and at L. And we have an initial condition that is non-trivial. So now that we have this, we want to point out that in general, the geometry of your domain dictates how difficult and complicated the solution is. So we started with the simplest possible domain. It's just an interval. When we will progress to more complicated domains, you'll immediately notice how the complexity of the solution really increases the more complex the domain you're looking at is. So we have set up the problem and we want to try to solve it. We are in 1D, so we could simplify the delta U by just giving U x. We're going to use an approach called separation of variables. We take an ansatz, that is a claim that we'll try to justify later on. We're going to test that the result does satisfy this claim. We're going to take an ansatz that our unknown u, that is a function of x and t, is actually a product of two functions, one only of x and one only of t. We have used this sort of separation of variable ansatz earlier on for ODEs, but here we really can think of x and t as being different variables. They're really indication of two different directions that you're solving for. Either way, we take u xt as a product of x function of x and t function of t. Then the derivative of u with respect to t is the derivative of capital T times x, and the second derivative of u with respect to x is capital T times x second prime. Notice that primes here have different meanings depending on which function you're taking the prime of. So t prime means t derivative with respect to time. X prime is capital X derivative with respect to x. So it's we call it notation overload. We're using the notation for it to be understandable, but you have to be careful in understanding what it means correctly. So we replace our ut minus alpha square uxx equal to 0. In the meanwhile, I set cv equal to 1. A rescaling makes also sense. And we transpose our ut minus alpha square uxx equal to 0 to t prime x minus alpha second x second t equals to 0. And then we do some reshuffling in order to have all the things that depend on time on one side and all the things that depend on x on the other side. So here we have t prime function of time divided alpha square, it's a constant, times t, that is also a function of time. All of this being a function of time is equal to x second, that is a function of x, divided x, that is a function of x. So you see that this is a separation of variables in the sense that all one variables are on one side and all the other variables are on the other side. And since this must be true for every x and every t, then it needs to be a constant fraction. So we can set this, either of these two fractions, both of these two fractions equal to minus k squared, where k is a constant independent of x and t. Now it might seem a bit odd that I'm choosing this way of saying that it's a constant. It will become clear how we are expecting k to be a real value, but in general, any number can be written as minus k squared if you allow k to be partially if you allow k to be complex. So allowing k to be complex in this setting allows us to write any number as minus k squared. Later on, we'll see that we can restrict ourselves for k being real, and we'll have reasonable solutions. But let's start with k being potentially complex. We went from having one PD to having two ODs. So from the heat equation in one dimension, we got to have two ODs, in each one having just one variable and one dimension. And ODs we have studied quite a while, so we should be able to solve these two things. Remembering that they are connected. In particular, in this case, they are connected through this k squared that is appearing in both situations and is supposed to have the same value. And we have boundary conditions given by the boundary conditions from our initial problem. So in this case, the boundary condition corresponds to having x at 0 times capital T equals to 0, and x at L times capital T equals to 0 for every time. So either we have t being 0 all the time, but that's probably a bit too much, because that means that everything is just trivial, or we have that x, capital X at 0 and at L is equal to 0. That is the more reasonable assumption. So this is the boundary conditions we will be using. So now we have two problems. A problem on x with two boundary conditions, and a problem on t with actually no boundary condition. Let's start with the problem on t because it's very easy. It's a first order ODE on the time that goes from 0 to infinity. We can easily solve it by the standard practice. So t is a t0, a constant, times exponential of minus k squared alpha squared t. And here we can start looking at k a bit more strictly. What do we want k to be? So this is an exponential. We need something up there that doesn't explode over time. So physically, we are expecting T, the temperature, to be bounded. So if K is complex, then K squared has a negative real part then minus k squared has a positive real part, and therefore exponential of minus k squared alpha squared t increases exponentially. This is unphysical, we don't want this, so we are expecting k to be real and k squared to be strictly positive. On the other problem, the second derivative of capital X plus k squared x equal to 0 with zero boundary condition 0 and L is a Sturm-Liouville problem. So we can solve it as we have done the Sturm-Liouville problem. Now we have k squared that corresponds to the eigenvalue of our Sturm-Liouville problem. So the first step is just solving the second order ODE, and we retrieve that the solution, capital X, is a composition of exponentials. On one hand, I have C1e exponential of ikx plus C2 exponentials of minus ikx. And we impose the boundary conditions, so we need C1 plus C2 is equal to 0 because x at 0 is equal to 0, and x at capital L is also equal to 0, so we need C1 exponential of ik capital L plus C2 exponential of minus ik capital L is equal to 0. We can write it as a matrix problem. So this matrix is 1, 1, exponential of ikl, exponential of minus ikl, and this matrix multiplied by C1 and C2 vector is equal to 0. If the determinant of this matrix is different than 0, then we only have the trivial solution. Then our capital X is equal to 0 all the time, and our solution of the global PDE is trivial. That's not very interesting. So we want to impose that the determinant of this matrix, that is exponential of minus ikl minus exponential of ikl, should be exactly equal to 0. So we have non-zero solutions of our matrix problem. In order for this equations to be satisfied, well, then k needs to be real. Actually, we need something stricter, because what we need is the sign of kl being equal to 0. So if you solve for it, you actually find discrete values of k being n pi divided by capital L for any natural number. Actually, we can take any integer, but it doesn't really matter, because negative n gives the same eigenvalue, because the eigenvalue is k squared, and the same eigenfunction. So we're good. We have found the eigenpair of our problem. To summarize, we have started with a 1D heat equation. We took the ansatz that our solution is a product of two functions, one depending only on x, one depending only on t. We solved the Sturm-Liouville problem associated with this ansatz on the x. We found a discrete series of eigenpairs, so eigenfunctions and eigenvalues. The eigenvalue is kn squared. And for every value of kn that we have found, we have a solution for t as well, capital T. So now, for every integer n, or positive integer n, we have a solution that is a product of tn times xn. That is something that depends on kn, on t and x. So it's exponential of minus k squared n, a squared t, all of this multiplied by the sine of kn to x. Let's check that what we have done up to now actually meets the demands of our situation. So does our un solution satisfy the heat equation on omega times 0 to infinity? So are we doing the full loop? We can check, And yes, the first derivative with respect to time times the second plus the second derivative with respect to space have a difference of a factor alpha squared. So yes, they satisfy the heat equation. Do they satisfy the boundary conditions? Trivially, because sine k and x satisfy the boundary conditions. So any linear combination of un solves the PDE, excluding initial conditions. So what we're left with is that u can be written as an infinite sum of some coefficient Cn times un. And it does satisfy the equation and the boundary condition. So the only thing we're left with, if it needs to satisfy the initial condition, we need u computed at x0 being equal to f of x. So we can rewrite this as the infinite sum that we have imposed. And at un x0, then the time dependency disappears and we only have the sine component. So we need to find Cn, all these coefficients, infinitely many coefficients, with this equation that puts together our initial condition on one side and our infinite sum of components on the other. And we can do this because this is one of the things our Sturm-Liouville theory can help us with, is actually finding the Cn's. If you notice, this is a sine Fourier series, so you can use that approach, but as a general statement, we have found the sines k and x as orthogonal eigenfunctions of a Sturm-Liouville problem. So decomposing any function f of x in this infinite sum can be done by the Sturm-Liouville approach by setting Cn equals to inner product f sine k and x divided by the square of the norm of sine k and x. That is inner product sine k and x times sine k and x. With the inner product being defined by the Sturm-Liouville problem we have introduced, that is just integral from 0 to L of the two functions f and g that you want to take the inner product of. So this is the complete solution. We can write the solution of our PDE as an infinite sum of a coefficient times un, where un is built on the ansatz of separation of variables. And this breakout into infinite components satisfies the PDE and the boundary condition. Then, in order to satisfy the initial condition, we impose that Cn satisfies the division between two inner products with the boundary, the initial condition f explicitly taking part in this